So you have a language and you want to construct a CFG for the language. Okay, so this is actually a fairly challenging problem. Okay, so everything we've done so far is I give you a CFG, I give you a context-free grammar, and then we can play around with it. We can see what strings can be generated, we can ask properties about what are those strings that are generated, and so on and so forth. But here's a much more challenging problem. I give you a language. So let me give you a language, and I have to describe it in some way. So let's say my language is strings with equal number of zeros and ones. Okay, so let's call this language of balanced strings. Okay. So you can think of this as, so what are some example strings in here? Okay, so for example, 0, 0, 1, 1. Okay, that's similar to that would also belong in the first language that was the problem for the DFA that we started with. But also 0, 1, 1, 0 would be in here. Okay, and so now we're trying to construct, a context-free grammar for this language. Now, it requires a little bit of creativity. There's no way around that. Okay, but we can sort of describe some, methods for approaching such a problem. Okay. And the basic idea is to start, because there's this relationship between context-free grammars and recursive definitions of sets. So the basic approach that I'm proposing, that I'm suggesting to you, is if you're asked to construct a CFG for a language, try to think about how to recursively define the strings in the language. Okay? So let's take an example of a string in this language. Okay? And it's a, reasonably complicated language. So here's an example of a string. Let's say 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0. Okay. Let's see if it's in this language. Does it have the same number of zeros and ones? So how many zeros does it have? 1, 2, 3, 4, 5, 6. How many ones does it have? 1, 2, 3, 4, 5, 6. So this string is in my language L-balanced. Now, if I'm trying to develop a recursive definition for this language, what I have to try to do is I have to try to relate this string to smaller strings in the language. So I will observe here, okay, now this is where the creativity comes, okay? So I will observe here that, any string in this language either starts with 0 or it starts with 1. And this is the case where it starts with 0. Okay, so this is equal to 0. Okay, now since the language is balanced, there must be a 1 somewhere. Because it starts with a 0, there must be a 1 somewhere. So there's a 1 somewhere. Okay, and I'm going to highlight a particular one, this guy. Okay, so I'm going to highlight this guy. Okay, and so there's a 1. We know there's at least one 1. Okay, so I've highlighted that one. Okay, and there's a 0. And in between here, so the reason I highlighted this guy is I noticed that in between here is a balanced string, 2 1s and 2 0s. Okay, so there's 1 0 1 0. Okay, and here afterwards is a balanced string, 3 zeros and 3 1s. So we have 0 0 1 1 1 0. Okay. And now if you sit and think about it, you will realize that this is always possible. For a balanced string, let's say that it starts with a 0, it must be the case, always, now sit down and prove this, that if it starts with a 0, there's a 1 somewhere, and here we have a balanced string, and here we have a balanced string. Okay. And if I'm going to use a start symbol S to represent strings in this language, so S is going to represent strings in this language, then this guy can be represented by a string in this language, and this guy can be represented by a string in this language. Okay. So what this suggests is that every string in this language can be represented as a 0 followed by a string in this language, followed by a 1, followed by a string in this language. Now, we do know that the empty string is in this language, so my start variable can go to the empty string, or a 0 followed by a string in this language, followed by a 1 followed by a string in this language. Okay. And that takes care of the strings that start with 0. The same argument holds for the strings that start with 1. So it could also be represented, it can also transition to the strings that start with 1. So a 1 followed by a string in this language, 0 followed by a string in this language. So I just flip the 0 and the 1. Okay. And here is a context-free grammar, that's for sure. Okay. And based on this rationale, okay, this rationale suggests that this context-free grammar will generate all the balanced strings. Okay. So, there, I've derived the grammar. Okay. Now what remains is to prove that it works. And that's the hard part. So, prove that it works. Okay. So, what needs to be proved? So I'm going to give you the high-level idea. And, okay, induction is going to be the main tool to use. Okay, so induction. But here are the basic two things that need to be proved. One, every string generated by this language is balanced. Every string generated by the CFG is in L balanced. Okay. Now, what's the idea here? The idea here is that let's look at what can be generated. Okay, and that's where the induction comes in. So, what can be generated? Epsilon. Well, that's clearly balanced. Okay. So, if you imagine that you run this context-free grammar for a certain number of steps and you've generated stuff. Okay. Now you're going to run it for one more step. Well, what does that one more step do? That one more step is producing, a string and a 0, 1. Okay. So it adds a 0 and it adds a 1. Okay. So each step is adding the same number of zeros and ones. Okay. So each step in a derivation preserves this property that the number of zeros equals the number of ones. Okay. And so that's the basic idea behind proving that every string that's generated by this language will have the same number of zeros and ones. If the first string that you can generate, has the same number of zeros and ones, and each step in this in the production rules, each of the production rules preserves this property, then everything you can generate will have that property. Well, the formal proof is by induction, okay? And you can see that in the text. So every step, produces a string which has S, okay, which by the induction hypothesis you can assume. So if I'm trying to derive a long string, these are shorter strings, okay, which we can assume satisfy the property, and then I'm adding an equal number of zeros and ones, has S's and an equal number of zeros and ones. Okay. So that's the basic idea behind why every string generated is going to be balanced. The other thing that has to be proved, and this is important to realize that two things have to be proved. The other thing that has to be proved is that every balanced string can be generated. Every balanced string can be generated. Okay. And what's the idea here? Let's consider a balanced string. Well, this sort of structure of any such balanced string becomes crucial. So any balanced string, let's suppose it starts with a 0. So any balanced string is of the form 0, x, 1, y, where this is balanced, like this guy, and this is balanced. Now we want to prove that this long balanced string can be generated. Okay? But this is a shorter balanced string, and this is a shorter balanced string. Okay? So by induction, these shorter balanced strings, so this would be an example of strong induction, these shorter balanced strings can be generated. Okay? So you start the generation process with S goes to 0, S, 1, S. Now this S can generate X, and this S can generate Y, and so that means that this string can be generated. It's again another induction. Okay? So induction, induction. Those are the two basic ideas behind proving that this grammar works. And how did we get this grammar? That's where the creativity comes in. To think, okay, how could I recursively define the strings in this set? Okay. Now, let me show you some of the power of, context-free grammars. And let's